Okay, guys. We'll try to get started. Is there a question over here?
Yeah. So I was looking up the official name for alkenes, and then I've seen sometimes it would say like, so for instance, if you have 2-pentene, I've also seen it named as pent-2-ene for this class, but it doesn't really matter between you.
Yeah, sometimes you put the 2 sort of in the middle of the name, pent-2-ene. You do that more often when there's extra stuff in front. 2-pentene is pretty standard. I would just do that. But that's acceptable also. Okay, we'll see where we're at. We are doing alkene reactions. We do have a handout today. Light sound in you? Oh, it was a little dim. So we got the white written handout and we got the purple outline. There's a handout today. The handout's coming around. We got about a minute before we start. Other questions before we get started?
No, you have a question.
Oh, I'm sorry. Yeah.
Okay, so like, do we say one cyclohexene or just cyclohexene?
It's not one is not needed.
Okay, so
In a ring, the double bond is the 1-2 position. Yeah. So it's redundant. Important thing to ask yourself is there any ambiguity if I don't say one? Okay? And if there's no ambiguity, then you don't need it. It's like 1-chloroethane. You don't need it because there's no such thing as 2-chloroethane. If you think about it. So you just say chloroethane. No, you won't get marked up if you do put the 1. Question?
This product right here, you mentioned that it would be in like a 48 to 52 ratio? Or something
Well, I was
like
just
that.
saying, when we say something is regioselective, it does not necessarily mean it's 100% to 0%. If something is 51% this one and 49% that one, that is actually regioselective because it was more selective for one than the other. But usually when I say it in here, it means we have a larger preference for this other one.
Well, I was going to ask, is it due to induction? Like, are the 2 different products of this have different induction, or does it not matter since they're branch?
No, they're both going to be secondary carbocations in that other one. So there's no preference. Would you rather form a secondary cation or a secondary cation? Okay, there's no preference. So you're not going to get regioselectivity. You're only going to get regioselectivity when you got a choice between like a primary and a tertiary. And if you do, which one are you going to form? Tertiary. Okay, let's get started. Remember the outline on the purple? Okay. By the way, going around right now, the pink, everybody gets a pink sheet today? The pink is a puzzle. Everybody got one? Okay, there should be a couple of floating around. There should be enough. Electrophilic addition of alkenes. This is a good review. It's a puzzle. There's a number of line reactions. Predict the product. Each one has a number associated with it. Each product has a letter associated with it. So for example, when you answer question number 1, you choose the answer and you get a letter and you put the letter right there. And you answer the riddle. The riddle is, how is the alkene able to learn all of its electrophilic reactions? Well, the answer is because and, well, that's an and, so that's not going to be a vowel. Because something, something. Okay? 3 of these reactions I do not cover in organic 1, cover in organic 2, and I already gave you the answer. Okay? Organic 2, I cover those. So by completing this puzzle, you can, or the questions, you can answer the puzzle. Okay, so that's just a little bit of some problems for practice. Purple sheet, we have our outline. Okay. Alkyl halides. Okay. Organization of the material. For example, what can you do in an alkene? You can hydrohalogenate and make an alkyl halide. You can hydrate it and make a alcohol. Okay, so what can you do with alkenes? That's one thing to focus on. The other thing to focus on is, hey, tell me a way to make alcohols. Hydration of alkenes. So there you're saying, how do you make alcohols? Tell me a way to make alkyl halides. Hydrohalogenation of alkenes. So you both ends, okay? What can you do with alkenes? How do you make alcohols? Now later on, we'll see a lot of ways to make alcohols. But right now, the only way you know how is to hydrate an alkene. Okay? So different ways to organize your thought process and to question yourself. Okay, let's continue on. We left off with something very exciting, I know. Where is it at? Predict the products below at the bottom of alkene, hydration of alkenes, is that right? Down here at the bottom. Predict the products. Okay, we got an alkene. What are we reacting the alkene with? Water and H+. Everybody agree? Okay. Now this is generic. That has to come from a strong acid. What does it look like we're doing to the alkene in general? What reaction we're doing?
Hydration.
Yeah, hydration with water and acid. Don't give an alcohol, right? Okay. What's the electrophile? That is, what does the alkene react with first? Proton. Okay, H+. It's okay to just show it like that. All right? 3 protons, okay. Where does it come from? There's got to be a minus there. What's the minus? Well, it's not shown. There's got to be a minus there. You can't just put plus in the flask. You've got to have a minus also. Some acid, like sulfuric acid, or phosphoric acid, or HF. Those are the 3 main acids for hydration. You don't want to use HBr here. You'll get hydrohalogenation. Okay? This is sufficient. Mechanism, what happens? The electrons in the pi bond, the electrons do what?
Attack.
They attack the H+. Okay? Are we going to pull away from left or right? Correct. We're going to take these electrons and we're going to hinge it down. We're going to go whoop and make the bond to that H. Pull them away, make the bond to H, and we're going to get, all right, 5 carbons. Which carbon is now bonded to H? Left or right?
Right.
Correct, the right one. Leaving this over here without a bond, plus charge. Okay, so there's your carbocation intermediate. What attacks the carbocation?
Water.
Water. What else can attack it? I mean, even if you had HSO4 minus here, what did I tell you about that?
Water.
That will never attack anything in this class. Never use it. Okay? It just supplies the H. It's spectator ion. Water attacks. These electrons do what?
Fine.
Bond here, what does that give? That gives a bond between lone pair to carbon. Nothing else is happening. Boom, 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 boom. I'll keep drawing in the H. We now have an oxygen there. That oxygen's got two H's though, right? I haven't lost those. There's one lone pair left. That lone pair is now bonding. If you take count of everything, that's now a plus charge on the oxygen. On day one, we talked about typical bonding for oxygen. 2 bonds, 2 lone pairs. That ain't typical, so it's got a charge. What's next? Something takes the H to go neutral. You can use water or that. Either one you want. That's not even shown. Okay, it's shown very generically. We can just use water. These electrons bond to the H. What do these 2 electrons do? Going to oxygen as a lone pair, what do we get? That gives us final product which looks like that. OH, 2 lone pairs, and what did we reform? Yeah, that's actually catalyst. I mean, now there's a proton that's available. There's an acid now available again. That's an acid catalyst. It's water and acid catalyst. The formula now has water added to it. Acid catalyst was regenerated. We made an alcohol, a secondary alcohol. We would not make the primary alcohol here because you would not make the primary carbocations. Okay, all that we did last time, right? Just to review. Question?
So do we, even though it's a catalyst, do we draw it form on the other side? Like as a product?
No, it says predicted product. The predicted product is typically the main organic product.
Okay.
I'm just showing that for clarity of what's going on. Okay, stereochemistry. Let's address this. In the stereochemistry, we could address last week, Tuesday, whatever. Okay? It's just I'm choosing to do it now. Don't think that it wasn't applicable before. Okay, stereochemistry. Let's back up over here. Carbocation, what's the hybridization of that carbon?
2.
How many H's on that carbon?
1.
There is 1 H there, okay? Right there, there's 1 H. That is sp2. What's the geometry? Trigonal, the important part is planar. It's planar. So when the water attacks, now let's look at it. What's the hybridization of the carbon now? It's now sp3. Okay, now it's tetrahedral. Okay? There it's planar, this is tetrahedral. Tetrahedral means 2 in the plane, 1 forward, 1 back. Let's draw this forward and back. I'm going to take this space right here. Let's forget about that H there, okay? It's there. I'm actually going to draw this one in. No, let's do it like this. Instead, let's draw the true geometry here, tetrahedral. True tetrahedral is 2 in the plane. I'm going to put these 2 in the plane. This guy has to be either forward or back. I'm going to draw it forward. Draw it forward. It'll look like that. Actually, let me just draw the final product. That's forward. And this is back. That means if all this is like this, this OH is coming out towards you. But if all this is like that, that's actually going, I can't put my pen behind the board, but if the board was here, it'd be going back like this, right? That's what the dash means. Okay, I could have drawn it here. Whatever you get here, it's the same as the end. The question is, which one of these do you get? You get both. Why do you get both? But it's not just rotation. This is not for rotation in you. That answer seems like you think these are the same thing. Who said they rotate? No, did you say they rotate?
I would assume, well, we've learned sigma bonds can rotate, so I don't see why it wouldn't be able to rotate around.
Well, they can rotate, but it would not, if you rotated this, you would not get this. Because, well, pretend that's in the plane. I can't really do it. If I rotate this and make this forward, this is going to be up. But here's down. They're, yeah. We're not quite there yet, but they're not the same, and rotation would not make them the same. These we will call later on enantiomers. The important question right now is which one do we get? And the answer is both. You get both of these. Why do you get both of these? It has to do because the cation is planar. I agree with that? Let's make a let's make a cation. There it is. And it's planar. That means it's flat like a sheet of paper here. Okay? There it is. It's got a carbon here, it's got a carbon there, and it's got an H straight up. It's all planar on the sheet of paper. Now there it is. Now what attacks it? Water. Okay? Water's in the flask, this is in the flask. The water, boom, attacks it. Let's keep it like this. If the water attacks from this side, the bond's going to be from that side. And you'll have which one of these? The one with the water bond coming forward. But see, all this is, this could also attack from the other side. If it attacks from the other side, you got the OH, the oxygen bond back. And it would be that. Okay? I mean, in a flask, you've got a gazillion of molecules. They're all mixing around. It's like if I went out here and said, okay, attack. Well, look, half of you attack over here, and the other attack will attack over here. Now, of course, if I went over here and said all of you attack, well, you would all attack to this side. But in a flask where everything is mixed and everything is dissolved, you're not going to have just this molecule over here and not, okay? It's basically random chance. Either side, you're going to get 50-50. This is a 50-50 mix. Later on, we will call these enantiomers. And your book abbreviates that as EN. Enantiomers. And later on, when we have the possibility of this at a carbon, which is chiral, I will highlight that with a little star. And we will call this racemic. What does racemic mean? It means 50-50 mix of enantiomers. Why do you get both? Because it attacks from either side, and randomness leads to 50-50. Attacking of what? The planar carbocation, right there. Because now it's tetrahedral. And now you have to have one forward and one back. Take home. Whenever you attack a carbocation, which side do you attack? Both. You attack both sides. Because it's planar, you attack both sides, you're going to end up with a 50-50 attack. Bonds are going to be one way, as if the nucleophile came in that way or the other way. Okay? So that's the take home. And next week, when we attack carbocations, how are we going to attack them? Both sides. And in 3 weeks, when we attack them, how are you going to attack them?
Both sides.
Okay, and in organic 2, when you attack them, how are you going to attack them? All right, don't forget it.
So all carbocation products are racemic?
Do all carbocations?
Produce racemic products?
I just hate to answer absolute questions like that, but I think pretty much, yeah. Now, there'll be a difference. Maybe today, maybe next time, we'll do some attacking, but we won't attack a carbocation. We'll attack a carbon that has a leaving group on it. That type of terminology. When you do that type of attack, you only attack backside. We haven't got there yet. But we know when you attack a carbocation, you attack both sides. Okay? Because it goes from planar and then it becomes tetrahedral. So that's the stereochemistry to consider. In the end, there's your alcohol. It is racemic because that's a chiral carbon. That's coming next week and then 2 weeks. The stereochemistry is going to be intertwined with these reactions. I sort of just give you tidbits along the way. Okay, reaction down here. Let's do this one pretty quick. HF is one of those strong acids that just is going to be acid. The F minus is not going to attack, so this is just your H plus source. The only reaction we know so far of alkenes is them attacking what? H plus? That's all we know so far. And when this attacks H plus, where are we going to leave cation, left or right? Correct. So this hinges the way we're going to get a cation. New H there, right? Cation here. It's actually 2 H's there because there's one there to begin with. What attacks cation? Does the F minus attack? No. No. We said sulfate, phosphate, and F minus don't attack in this class. F minus loves the electrons. It doesn't want to let them get out there and do anything. It holds those electrons tight. So what are electrons going to attack here? Ethanol. It's just like water. Analogous to water, just it has a carbon group on it instead of 2 H's. Otherwise, it's the same as that. These electrons do what? Bam. Nucleophile. We call this a nucleophile, right? Yep. Nucleophiles like positive charges. Nucleophile adds to the carbocation. What does that give? What does this arrow mean to you?
The electrons take that proton.
That lone pair is bonding to this carbon as a bond. Now, there's the lone pair. It's now a bond. There's one lone pair left. There's an H there, and there's an ethyl there. We didn't lose the H or the ethyl. What does my arrow show? My arrow shows the lone pair making a bond to carbon. That's it. And so that's all I can show. I can't show all these other stuff because if I did, I didn't have the arrows for it. That arrow gives us this. Now there's a charge here. Positive. Because if a positive reacts with a neutral, you should have a positive. So find it. Okay? That's an atypical oxygen. All right, the F minus would like to have its proton back because ultimately the HF is going to be a catalyst. It wasn't written there, but you kind of have to figure that out. Because to go neutral, the oxygen is going to lose, it's not going to lose the ethyl. Okay? We can lose an H in an acid-base reaction. The F minus does what? These electrons do what? They bond to H. What do these electrons do? We're going to move these onto the oxygen, and what do we get? We're going to get an oxygen with 2 lone pairs and an ethyl group plus HF reformed. And since it's reformed, we can call it catalyst. By the way, if you have a catalyst, usually it participates in the very first step. The very first step was reacting with the H plus catalyst. Questions?
Is the difference in electronegativity between F and Cl the reason why HF can be a catalyst and HCl can't be a catalyst?
But chlorine will attack here and give you an alkyl chloride.
Even if it's in the same example there with ethanol and HCl?
Chlorine is more likely to act as a nucleophile. F minus will not act as a nucleophile, especially in this class. Why? It holds on to its electrons tighter. It's hard to explain other than that. But we know in practice that F minus doesn't like to add to cations. Okay? It's called a hard anion. You can look that up. It's not a good nucleophile, typically. And what I say in this class, we're never going to use F minus as a nucleophile. Here, it's acting as a base. It's taking the H, call that acting as a base. So there we go. In this case, we actually did not make an alcohol. What did we make?
Ether.
Actually made an ether. But do we have to know that to begin with? No, you have to know the chemistry. I mean, this is just like water. You have to get over there and say, it is an ether. You know, I didn't know I was making an ether. But in the end, the third reaction up there, if you react an alkene with H plus and an alcohol, you actually get an ether. Okay? So the ether will add, the alcohol will add, and that's actually an ether product. But don't memorize that. Learn your mechanism. Just work through it. There's your ether. Questions? What type of reaction is it called?
It's like the middle one with the hydration.
Yeah, it's not as common. Alcoholysis? It doesn't have really a good common name like hydration or hydrohallucination. Ether formation from alkene. Okay. Yes. Carbocation rearrangements. Carbocations are prone to rearranging. I'll say that many times. That was the first time. If you take this alkene here, what is that? 3-methyl, 1-pentene? No, 1, 2, 3. 1-butene? 3-methyl, 1-butene? Does that look right? Yeah. If you take that compound, react with HBr, you get two products. First one, minor. Looks like they're both hydrohalogenation products. We added HBr to the alkene. But it's different regioisomers. In the first one, the bromine bonded to the second carbon, that region. In the major product, the bromine is bonded to the carbon next door, a different region. Getting the minor product is straightforward. Well, let's start at the beginning. What's the first step in the mechanism? We can show this ionic. Alkene reacts with H+. It's going to hinge away from the bottom and go attack. And we're going to get UH there and a plus here. Isn't that where you want to put the plus? You don't want to put it on that carbon, do you? If you put it there, that'd be a primary carbocation. Here it's secondary. Okay. Now the Br minus can attack there. And what does that give? That gives a minor product. Yes, there's a new H there. So we added HBr across the alkene. That's a minor product. So I'll call that A and this A. The A arrow goes to that way. How do we get to major product here, though? Well, if you go over here, it is okay to say, hey, if the bromine bonded there, there must have been a cation there. So that's the only way we know to get a bromine bonded there. So it must have been that cation. And if we have that cation, we can envision the last step being the bromine doing that. If we have that, we can show a mechanism for that. Can we go from there to there? Can we go from this cation to that cation? What's the name of this page?
Rearrangement.
Rearrangement. Can we rearrange this cation? Apparently so. What's going on when it rearranges other than the plus ending up here? There's something that's moving.
Hydrogen.
How many H's on this carbon? 1. That's that same carbon. There's 1 H there, right? So it's like you got these 2 methyls on a carbon. That one's got 1 H. 2 methyls on a carbon. Hold on. Still 1 there. 1 H there. I want to look over here. How many H's here? 1. Yeah, there's 1 there, undrawn.
1.
How many there now?
9.
0.
I don't know if I just looked at the wrong one, but there's 1 there, there's 0 there. Yeah, I think I looked at the wrong one. There's 1 here. So how many here? 2. So there's 0 and 2. Where over here there was 1 and 1 in terms of H's. What looks like might have happened? H moved. Okay? There's an H here. I'm going to draw it in. Okay? It's going to be kind of an ugly bond angle, but there's an H there. There's 2 here now. Really need the H's in. So here's the 1, 1, and there's the 0, 2. What will happen here is these electrons here, this is a sigma bond, H carbon sigma bond. But those electrons will actually become attracted to the plus. I'm going to show it to you and then we'll discuss it more. What happens is these electrons actually break away from that carbon. It's like they're here. I'm going to show an arrow where I break them away from that carbon and go bond them over there. I'm going to do something like this. What does that arrow movement give? It gives that. The H and the 2 electrons break away and go over there and bond over there. So this H and electrons used to be bonded here, but it broke away and it moved and now it's bonded over there. Now over there now has 4 bonds and that's neutral. But over here is now missing a bond and so it is positive. So this is called a carbocation rearrangement. And that's at the top of the page, right? Carbocation is rearranged. Sometimes it's called by a skeletal rearrangement. Question, Larry?
Yeah, the tertiary carbocation this number is more stable than the secondary.
Good. That's the next thing I needed to say. What type of cation is this? No, that's secondary. Secondary, right? What kind is this? Tertiary. Why did it rearrange? It rearranged to a more stable cation. Okay? Now this is sigma electrons sort of attacking something. Here we go. I'm the H. I'm bonded to this carbon. All right? And you're a carbocation. All right? These electrons start liking that carbocation, so they're moving this way. And eventually they just somehow, this is Mother Nature, okay? The electrons break free and like, okay, see you later. And go over there and bond to there. And so now you're a carbocation and now you have a full octet. You have 4 bonds. Why did that happen? Because you're a more stable cation than she was. Now, I see a lot of students will do something like this, like the H moves over here. You got to importantly know the two electrons move also, okay? I'm moving the electrons, not the atom. So I'm moving the H and the two electrons. What do we call H and two electrons? Now, if H has two electrons, it's a minus. What do we call that?
Hydride.
Hydride. Yes. This is a hydride shift. The hydride shift leads to carbocation rearrangement from a secondary cation to a tertiary. Carbocations are prone to rearranging if they can rearrange. One way is by hydride shift. Now we can get more specific. It's called a 1,2 hydride shift. Because if this H is, if we call that the 1 carbon, it moves to the second one, the one next door. Now this may be the only type we ever see. If you get to advanced chemistry, you might see some fancier shifts like the 1,5. Like it's bonded here, and instead of it bonding next door, it ends up bonding way over here. I don't think we'll see any of those. But you understand what the 1,2 means? Basically, if that's 1, it moves next door to the 2. Question?
So does the carbocation, that positive charge, isn't it be adjacent to the hydride shift?
What do you mean will it be adjacent?
Does it have to be adjacent in order for it to be a shift?
The ones we'll do, they'll be adjacent. The advanced ones, they can become a little more, yeah. Question?
When you call it a 1-2 hydride shift, is it just for this example? Because when you name it 1, 2, 3, or is it just?
It has nothing to do with the naming.
Oh,
Just-
okay.
the first carbon is called 1, and we call the next one 2.
Oh, okay.
That's it. So nothing to do with the naming.
Okay.
It's just a relative positioning. One's there and it moved next door, we call that 2. If it did a jump, it'd be 1, 3. Okay. So, if we do a carbocation rearrangement, how do we get the major product now? We've already shown that. Now the Br minus, which was watching this, now attacks and boom, you get your major product. Why is it major? Well, it really all depends on how fast does this take place. If this is slow, you might get a lot of bromine attacking here, and you might get this to be the major product. The faster this rearrangement is, the more you're going to get of this product. For us, to make it more clear, anytime you can do a carbocation rearrangement, do it and call it the major pathway, major product. Okay? Always do a rearrangement. When do you do a rearrangement? When you can go to a better cation, like secondary to tertiary or primary to tertiary. You're never going to go from like tertiary to secondary. You wouldn't go the other way. Let's try another one below. If you take this alkene here, react it with aqueous acid, looks like we're doing a hydration of an alkene. This alcohol is the minor product. The major product is actually this guy over here. By the way, there's lots of applications of carbocation rearrangements. I'm not 100% certain, but I think when your body makes cholesterol, I think there's a carbocation rearrangement that takes place. Okay. Lots of this. Carbocations are prone to rearrangement. What do we got here? What's the electrophile? H plus, right? These electrons attack H plus. Make cation here, right? All right. Nothing new there, right? Water can attack here. And then after you lose the proton, which product would you get? You get that, and a new H there. Let's just do the mechanism for the major product. What happens? It looks like we need That cation. If we have that cation, could you show a mechanism for forming that? Well, it won't be directly, but we can get there. Water attacking and then losing proton. So how do we get this cation if we started out with this one? Can we move an H over? This is an example not of a hydride shift. Here we're going to move a methyl over. It's the same way though. The electrons will break free and the methyl will just move over. What do you want to call a methyl group? What's generic for methyl? Or ethyl or propyl? Alkyl. And since it's going from here to here, we'll call it a 1,2 alkyl shift. And what does this arrow movement give? This carbon has this methyl. See, that H just looks funny. See, that's a methyl. There's two other H's there. But now when this moves over, there's two methyls. Where's the plus charge? I don't know that one's plus and not this one. Because there's an H there, right? You got to know where your H is. There's an H there. There's 3 bonds there. When this moves over, there's 4 bonds there. But here there's no H. When that moves over, this carbon only has how many bonds? 3. So the plus is there. There's an H here, right? So this is an example of an alkyl shift, where the carbon breaks away and says, I like that cation better. Or, okay, sorry, I'm going over here. And the electrons start attracting, they break away. Okay, because you're a better cation. What do? We went from secondary to what? Tertiary, better cation. So if we plotted an intermediate, which intermediate would be lower in energy, left or right? Obviously the right, yeah. We're going downhill. So this is thermodynamically favored to rearrange. It's called a skeletal rearrangement. Carbocation rearrangement. Question?
So from now on, when we're drawing any mechanism, we need to examine if there's a more stable configuration and just draw that, or do we need to draw both major and minor?
All depends on what you're being asked. If you're asked to predict a product, I would always choose the one. What I want you to do is choose the one that had the carbocation rearrangement, which is a better cation. We'll do more examples. It'll hopefully become clear. Okay, water's hanging around, launching this. What happens now? Oxygen makes bond to carbocation. These electrons bond to carbon. What does that give? O. We haven't done anything to the H's or the other lone pair. That's a plus. That arrow movement gives this. Now what do we need to do to get this?
Water.
Something needs to take the H. What do you want to take it?
Water.
Water. If I'd showed a minus here, if I'd shown sulfuric acid, I could use like bisulfate taking the H, like we did last time. These electrons can do what? Bond to the H. These electrons bond to the oxygen. We get oxygen with 2 lone pairs, and we reform what? That's basically H+. H+ reform. H+ was the catalyst. So I actually used 2 waters on the board. Only one of them reacted with the molecule. So carbocations are prone to doing what? Rearranging by 1,2 hydride shift or 1,2 alkyl shift. Now we can do some other rearrangements called ring expansion or contraction. These are really just the same thing we just did, except there's going to be a ring involved. If you take this compound here with the 4-membered ring, cyclobutane, and the alkene coming off, react with HBr. The main product is this here with a 5-membered ring. Obviously, the ring has expanded, so we can call it a ring expansion reaction. How did it happen? The only reactivity you know thus far is an alkene reacting with H+. Do we have an alkene? Yes. Do we have H+? There you go. There's your beginning. These electrons react with H+. We're going to put cation on right or left? Here's your alkene on the board like this. Electrons break away from the bottom carbon and go take the H, leaving the bottom carbon plus. Why? Because it's secondary. Cation up there would be primary. That would not be good. Okay, Br minus could attack here, but that wouldn't give us that product. We need to show a mechanism for that product. This is a mechanism question. You got a cation. What are they prone to doing? Rearranging. I can move this methyl over. What if this methyl breaks free and moves over here? What would that give? This carbon has now 2 methyls. See, drawing in the H gets a little, one of them has a new H on it. The other one moved over here. So here, there was no H. There's no H there, so this is a plus. Does this get us to where we need to go, though? No. No, I don't. This is not going to get us where we need to go.
Put it in the ring.
That's A, this is A. See here, there's other things connected to this carbon. Instead of the methyl moving over, instead of those electrons moving over and taking the methyl with it, what if these electrons move over? That is, if these, and we take these and say, see you later, I'm going to go over here. Can we envision that? Envision these breaking away from the top carbon and just going over there. So I'm going to sort of say breaking away and moving that way and call that B. What does B give? I'm going to draw it just like I have it there. The new H is there. That bond used to be there, right? But now it's where? And now it's there. Now it's moved over there. So what is here now? Plus charge, because it lost the bond. So instead of the methyl moving over, instead of the electrons bonded to the methyl moving over, the electrons bonded to this ring carbon moved over. But now that's a 4-membered ring. What size ring is this now? 5. And if we kind of clean it up a little bit, it's going to be a 5-membered ring with 2 methyls next to each other, but one of them being a cation. So that is the same thing. And at that point, are we getting close to where we need to be? All we need to do now is what? Now the bromine, which was watching this, bam, what does this give? Bond to carbon, what does that give? That gives your final product. Why did this rearrange? What type of cation is this? The rearrangement, what do you want to call the rearrangement? We call it ring expansion. It's analogous to an alkyl shift, but it was part of a ring. So this would be like we make a ring. Let's make a 3-member ring, guys. All right. No, you're bonded to him. Yeah. No, y'all bonded. Okay.
They're bonded
Okay.
together.
Yeah, y'all need to be bonded together. Yeah. There we go. There we go. Yeah, y'all bonded too. All right. You don't have enough heart. But now I'm going to break away from you, and I'm going to go over here, pretend that you're bonded. But I'm going to move over. You're coming. All right. Boom. So it went from a 3 to a 4 because when I broke away and moved over, we expanded the ring. I know everybody saw that, right? All right. Break away, move over, but now the ring is bigger. Secondary, what kind we got now? Tertiary, that's a better cation, right? One reason. But there's another reason why it did this. What's another reason? Why is it preferred to do this?
Bigger rings, more stable.
What's the best size rings? 5 and 6. 4-membered rings got this ring strain because there's these 90-degree bond angles. 5 is like, opens up a little bit more like 1 to 9.5. Also relieves the ring strain. Okay, so this is dropping downhill. Mother Nature likes to drop downhill, right? Become more favored. All right, so this is your product. How do we know that's the product? Because somebody went to lab expecting to get bromine added here, and they actually get this. And so we have to explain why. But the explanation is very standard chemistry. Alkene chemistry, carbocation chemistry, rearranging. Another example below. Down below, we go from a 7 to a 6. So that's a ring contraction. I wonder how that happens. It's a big ring, but I say see you later. I'm going to break down to a smaller ring. Okay. You can do that one on your own?
No.
What's the first step? Yeah, the first step is kind of, you could go either way. You're going to make cation on top or bottom.
Make it on the bottom.
Either way would be secondary. Sometimes when you have a choice, you have to do kind of go down both paths and see which path is the right path. We get a cation. Sometimes it's good to go over here. Now with mechanisms, I'll say this a lot. One step at a time. Do what you know, do what you know. Don't try to do it all the way at the end. What's the first reaction? You know, do it. Then step back and think about, okay, what can I do next? But you can also look over here because hopefully you all agree that we need that cation. If we can have that cation, can you draw a mechanism for final product? Yeah, water would attack that and then you'd lose the H. So how can we get that product? This is a carbon with 2 methyls. We got a carbon with 2 methyls up there. And that's outside the ring. It's almost like this used to be bonded out there. And it moved here to a 6, a smaller ring. So that's kind of some thinking you have to kind of do. I want you to try this on your own because you need to have practice thinking on your own. Okay? And we'll come back to this next time. This is just when alkene reacts with the H+, what do you want to call that step? call it protonation of the alkene. There's going to be some type of rearrangement, and then you're going to get to this point, you're going to add your water, etc. Give that a try. That's going to be a ring contraction. Let's move to this next example. We do have our outline. Now what we just finished was Roman numeral 4. I'm actually going to skip 5 for a second. We're going to jump to 6. Roman numeral 6, polymerization of alkenes. Sorter. This is not exactly polymerization, but we're heading that way. So let's look at this reaction. If you take this compound with 2 alkenes, we can call it a diene. If you react it with HI, you get this cyclic compound here. 1,1-dimethyl 3-iodocyclohexane. How does this happen? Well, we got alkenes. The only thing we've reacted an alkene with is what? H plus? Do we have H plus? Yeah. Which alkene is going to react? The one that gives the best cation. Now if you got one alkene, you say, well, which carbon is going to give the best cation? If you got 2 alkenes, you can say, well, which carbon of the 4 is going to give the best cation? Where would you rather make cation? There, 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 there. 1, 2, 3, or 4? 2. Yeah. Hopefully you'll be rewarded by recognizing that. Let's have the H plus here. These electrons break away from that carbon, so they come like this. Let's do one step at a time, okay? That's going to give that there with the plus charge here. I'm thinking right now only about a third to half of you can get to that point. All right. You've got to sit down, you've got to look at the book, you've got to practice getting to that point. I don't know only a third to half because I've taught for 10 or 15 years. So you got to do the practice. Don't think you know it. You got to do practice. You got to make errors and then discover that you made the error. That's how you learn. Okay. If you never make an error, you're going to end up making them all on test day. Okay. What next? Well, if I minus added here, which we know we could do mechanistically, that'd give us a product, but it wouldn't be that, right? So what else could happen?
Carbon on the other side?
We got this alkene out here. Can an alkene attack a plus? Yes, it just attacked a plus there. Does it have to be an H plus, or can it be a C plus? It can also be a C plus. It has nothing to do with how many protons are in the nucleus. It has to do with it being a plus. The alkene could attack the plus. Now, this has to be able to swing around and rotate and do all this. Okay? I'm just going to rotate it around. What if I draw this? Don't write it. Let me see if I can get it drawn here. 1, 2, 3, 4. 1, 2, 3, 4. Boom, boom. Plus, and there's an H here. So that is that with the alkene arm just swung around near the cation. Now, And just pretend that I said H plus, C plus, same thing. These electrons can attack there. Now, if they do, or we're gonna form a plus on this guy. Or we're gonna form a plus on the left or right? On the right. So let's envision the electrons breaking away and swinging up there. Break away there and swing up there. What does that give? I'm going to draw this like, that used to be the alkene, but it swung up and now it bonded up there instead of there. And that carbon's got two methyls. Where's the plus? What used to be the alkene? The alkene used to be here. It swung up, so where's the plus? Right there? I mean, you can even number these or something, okay? A, B, C, D, E. D, E used to be the alkene. When this comes up, the plus is on D, right? A, B, C, D, correct? So there we go. That's just an alkene attacking the carbocation. Alkenes can attack C pluses just like H pluses. Because it's internal, we call it what? Intramolecular. What do we need to do to get home? You see how close we are now? Now the iodide, which was just watching this, these electrons, bam, what does that give? It gives the iodine bond, and there we go. One thing to note here is, which is faster? Iodine attacking here, or alkene attacking here? Internal is always faster. Okay? That iodine has to go cross country to attack here. Before it does, boom, the alkene attacks. Then the iodine comes in. Okay? Internal is always faster. All right, someone slap my hand. Who's gonna come slap? I beat you. Internal's faster, okay? I'm right here. Who wants to beat me? Somebody slap my hand before I do. That's faster. Internal's faster, right? You're too slow. Too slow. Internal's faster. Okay, so there's an example of attacking a carbocation. How about a polymerization reaction? If you polymerize ethylene, what do you get? You get polyethylene. What do you make with polyethylene? Plastic. All types of stuff. Like the floating in your pool. That's polyethylene probably. Let's look at this. If you take this alkene here, what do we want to call this? Propene? Why do I not need a number in front of propene? There's no such thing as 2 propene. If I put the double bond over here, is that 2 propene? No, that's 1 propene just flipped over. So you don't need a number, it's propene. If I take propene and treat it with H plus catalyst, I can get a polymer. And the polymer will look like this, and we have to know how to show polymers. How does this happen? Well, can an alkene react with H plus? Yeah. Are we going to make cation on left or right? Left. We're going to pull away, and we're going to get that. So the electrons break away and go make the bond to H, leaving this as a carbocation. Nothing new. All right, what can attack the cation? Now, I'm purposely not showing a minus here. You would not want to use HBr for this reaction because if you had Br, it would attack the cation. What do we want to attack the cation? What is a polymerization? It's this reacting with itself over and over. So how could this react with that? Have you ever seen an alkene react with a carbocation?
Yes.
Previous example. This reacts with that. So we don't want a competing nucleophile. We want this to react. Now when this reacts, are we going to leave cation on left or right?
Left.
Left. So this breaks away and tacks here. So this carbon bonds here. This is where you have to, okay, get it right. Let's do some lettering. A, B, C. Which carbon is bonding to the cation? C. It's hinging away and bonding to the cation, leaving cation here. So we're going to have A, B, C, leaving cation at B, right? Don't you want to leave cation there?
Yeah.
C's bonded here. Let's call that ABC. What's that then? D? E? F? C is bonded to what? E. That's E. The E has a D and F. And let's draw that original H there. I also like to highlight what bond we just made. Didn't we just make that bond? Because didn't that used to be the alkene of ABC, but it broke away and bonded to the cation, leaving B as a cation. That's no longer a cation. So now we have this. So now we got a new cation. Well, what attacks this? What attacks this? Another one. GHI. What are we going to do here?
Same thing.
Are we going to break away from H or I? Break away from H. These are going to come down here. So which carbon is actually bonded to B? I. So we're going to get GHI. I is now bonded to B. That's A, B, C, E, F. Which bond did we just make? I to what?
B.
I to B, right? See? The bond we just made. Where's the cation now? H, right? The electrons break away from H and went and bonded. I'm I. I broke away from H. I went and bonded to B, leaving H as the cation, right? Here we go. So C to E we made. Now we made that. Okay, what attacks this? Another one. How long do you want to go? It goes on and on. This happens a gazillion times, and you end up with a polymer. At some point, we got to end it because we don't have all night. Larry?
Yeah, you won't have a vat full of H pluses laying around. They have to be attached to some sort of molecule. What gets this thing started?
Like a trace of sulfuric acid. Yeah, there's got to be a minus. So there's got to be a minus there. Okay, you take propene, you add in just a trace amount of sulfuric acid, and it gets it started. But what do we say about sulfate in this class? It will never react with anything. So what's going to react with the cation it's formed? Itself. And it just keeps on. You would not want to use HBr as your catalyst because the Br minus would react and you won't get the polymerization. Question?
So then at the end, when you don't want to have any more positive charges, would it just like an H plus bond to it, or what would bond it?
Well, H plus wouldn't bond to a C plus.
Right, okay.
Okay? We don't know enough to end it. Okay? And also with the polymer chemists, they may not know enough. Polymer chemistry, the end of it is a little bit ambiguous from what I know. Okay? It'll polymerize, it'll turn into this hard product, and you can vary the conditions and get different hardness of products. At this point, getting into polymer chemistry, there's a lot of questions to ask like that. What do we need to know now is how do we get going, how do we get to this point, and how to show this. Whenever you have polymers, you want to think about what is the repeating unit in the polymer. The H is what got it started. What is H, a cation or anion? Cation. The cation started it. That's why we call it cationic polymerization. That's what starts it, the cation. If an anion started it, we would call it anionic polymerization. If a radical started it, we would call it radical polymerization. This is a cation polymerization because the cation the H plus started it. After the starting point, we can look for repeating units. And what we have here is a CH2 carbon methyl. CH2 carbon methyl. CH2 carbon methyl. And indeed, if I had drawn it out 10 miles long, it would have been CH2 carbon methyl, CH2 carbon methyl, CH2 carbon methyl. So what we can show is, that's it. It's an H only in, I just got it flipped around. After the H is what? CH2 carbon methyl. CH2 carbon methyl. CH2 carbon methyl, you see? So the repeating unit can be shown in brackets or parentheses. It's CH2 carbon methyl. Where N is some huge number like 100 gazillion repeating units all lined up. That's typically how you show it. And you know, this right here may be the only thing you see shown for the polymer. But how do you know that CH2 carbon methyl? Because you put it together mechanistically and then you look at it. Question? There was a question. Okay, so alkenes can be polymerized. Cationic is this example. Superglue, that's an anionic polymerization. Okay? Superglue is a liquid, but what happens if you put it on the table? It hardens. It undergoes a polymerization, but it's caused by base. There's base everywhere. There's base on the table, there's base on your fingers. Question?
Yeah. So with the cationic polymerization, do we just keep adding the proteins like?
Yeah, I mean, what adds here? Another propene.
So it's just added to the.
It does it a gazillion times. You know, I showed it to you 2 or 3 times. Okay. The other one we want to look at here is back up to number 5. And actually 5, there's 2 entries under Roman numeral 5. The first one we actually looked at before the polymerization. Okay? The second one we're going to look at on this page over here. Anybody know what THC is? Tetrahydrocannabinol. You know what it is?
I have.
What is it?
So gives you high marijuana.
Well, this is how it's made, right here. This is how the plant makes it. What's the name of the plant?
Cannabis.
Yeah, that's right. This is how it makes it, okay? First it makes this compound. Then this undergoes a reaction with H plus catalyst. What's going on here? Where's the chemistry taking place? And there's, what's the difference? Right here. You got this alkene, you got this OH. So now the oxygen is bonded to one of these carbons over here. Right? I mean, nothing takes place up in there, right? Okay. This is an example. This is another internal reaction. Okay. Intramolecular. But here, it's sort of a heteroatom nucleophile that's doing the attacking, the nucleophile. The oxygen is going to be a nucleophile analogous to water or alcohol. It just happens to be already in the molecule. Now, what type of reaction do you know so far? Alkenes reacting with what? H plus? Do you have an alkene? Do you have H plus? Where are you going to make cation, left or right? It's the same old questions. Eventually you're going to have a cation and a nucleophile is going to attack, but the nucleophile is already in the molecule, and when it attacks it's going to make a ring. Do this one on your own. This is the second entry under Roman numeral 5. Other nucleophile attacking cation within the same molecule. Question?
I know this is empirically correct, but why can't that tertiary carbon on the first ring up there, that tertiary carbon,
Up here?
yeah, why doesn't that attack rather than that like?
The H plus?
Yeah.
That's a good question. I mean, that's obviously an alkene. We know alkenes can attack H plus. But it didn't. You'll have to ask Mother Nature or the cannabis plant. Okay? Sometimes when you have diversity activity, sometimes it's hard to say. I mean, you could do studies and model it and do thermodynamics. Yeah. I mean, this alkene could react with H plus. But we recognize that apparently it did not. So
Does some of that have to do with actual endurance? Or
it would be a variety of reasons. A little bit beyond what we can discuss right now, but you know, it's a good question. Selectivity, when you have multiple possible routes, selectivity, that's hugely important. Mother Nature is very good at it. And usually organic chemists try to do it, and often fail. That's why we often try to learn from nature, and this would be called a natural product synthesis. Okay, let's see what's next. Let's set the stage, but you got two mechanisms, the ring contraction and that one to work on. First step in both of them is alkene reacting with H+. That's all we've done so far. Okay? Next time we're going to kick it up a notch, because we're going to start reacting with things other than H+. Let's look at the outline. Next time we'll be moving on to these reactions here. Roman numeral 2. Reacting with things like a little halogen like bromine, Br2. Bromine in water, chlorine in water. Peroxy acids. Diazomethane. Chloroform. Mercuration. B2H6, which in your book is probably called BH3. B2H6 is just a dimer of BH3. You need to be looking at these reactions in your textbook. Okay? These reagents. I forgot to mention, again, there's a lot of good scores on the test. The high was a 103. And each high test, I usually give a little token of appreciation. I didn't bring one with me, but I usually give a pocket periodic table. So congratulations to that. Hopefully other people can get pocket periodic tables next time. Have a good evening, guys. Some of you have lab tonight and tomorrow. See you soon.